Good afternoon. Yeah, so we've been seeing some presentations about everything happening on the in the street and all the way up to the front door for for customers, TV, data, etc. What I would like to discuss with you, and I'm going to stretch it a little bit more, not only wireless, but also tell you a little bit about, I heard Mocha already mentioned, a little bit more about the technologies for in-home distribution of data and video, because that appears to be quite a problem in the market and in the cable and also telco industry. So I also wanted to have, I guess you know that ARRIS acquired quite a big chunk of Motorola, the Motorola Home Division. So we used to be a cable, 100% cable company. Nowadays we also do telco. So from that perspective, for this presentation it was good because the telco industry has been a lot further along the way on the wireless gateway, and well, gateway as a concept at customers for many years already, where you now see the cable industry, taking up as well. They have been running with cable modems and EMTAs for a long time. So the two companies are now one. It will be ARRIS for going forward. We're quite a big company now, and we touch a lot of markets. So as a teaser, I mean, in Europe we have a lot less products. Of course, you can imagine we had to combine the cable CPE portfolio. You see here cable modems, EMTAs, gateways, etc. We have a bunch of those with all kinds of technologies, with wireless, Ethernet, all kinds of types, HPNA, Mocha, what have you. So we're going to drill down today a little bit about what is out there and what do we think as a company that the future will bring for us. So there is a bunch of home networking technologies around. I think the most best fit for anything we would like to do at home is a simple Ethernet, Cat5 or Cat6 cable. It is cost effective. Every product nowadays is carrying an Ethernet port when it is a fixed device. It can scale up to 1 gigabit easily. The problem is you have to run wires to the places in the home. So not many operators are in favor of doing that because it's labor intensive. Digging in the street is labor intensive, but also doing a lot of cabling in the home is. There are a few other alternatives that have been popping up and have already been gone through some iterations with regards to speeds. I might have a few slides because I had to pack it really quickly. There is some data that is overlapping, but for example, home plug, AV and AV2, power line. So the normal 220 or 110 volt cables in every home. You put a signal on it, and you run data over that signal. It sounds like great because everywhere you have a set-top box or a device, there is a power outlet anyway because you have to power it. So it sounds like a great solution. In reality, it has some drawbacks that it's expensive. It's extra adapters, and you also see that, for example, in some markets in Europe, it might be taking off a lot better than, for example, in the US. So HPNA is one that you probably haven't seen a lot. It's the phone line. It's more of a telco thing. You will see later on how the spectrum is being used. It's not really a high-speed technology. It can go nowadays with the 3.1, which I don't even think is widely available yet. You could go up to 300 megabits per second on the phi rate, but Mocha for the cable industry in the US seems to be a very nice way going forward. The reason, US homes, they are mostly based as a star, so coax cables going to every room where there is a TV set. And since there is a set-top box or a TV set, there is a coax cable. Why not run above the 1 gigahertz some data, bidirectional, high speed, low latency. I mean, the coax cable is good, so that sounds very nice. For Europe, it's a different story because houses are not built like that. Coax cables are not run to every room. It's not even always sure where the coax cable is coming in and going out in houses and going to second floors. There is a new initiative that is taking up now. It's called G.hn. It is an ITU standard, and actually what they're trying to do is to have the home plug, the HPNA, and the MoCA technologies. I mean, the different media that they're running on to put on one technology, and then independent of what kind of wiring you want to use. Now that sounds great, but you know that in CPE space, modularity is killing because it involves extra cost. So I don't know how G.hn is actually gonna be taking off, because you cannot have an easy way of combining either using power line or telephone or coaxial on this technology. And then the last one, and that's the one we will dig in a little deeper at the end of the presentation, is of course Wi-Fi. I mean, right now Wi-Fi has had multiple iterations, and we'll see that it's getting to a point where actually it seems to be hitting the 95% of use cases where it actually can be used. So the playing field in frequency. You see here that in the air we have a lot of stuff happening on 2.4 gigahertz right now. Basically B, G, and N wireless are in that space. N and the new AC, as well as the older A version, has been around in the 5 gigahertz space. The problem with 5 gigahertz so far has been that one wall in between and your signal was basically gone. So the 2.4 was being used a lot more because it had more reach, and it turned out that reach was of course important. On the coax, as we discussed, it could from MoCA, it goes in this picture all the way from 850 all the way up to 1.5 gigahertz. So it should be not affecting your current DVB signals, DOCSIS signals, or analog TV signals. The power line, well, it's nice and clean because there is only 50 hertz or 60 hertz signal on it, which is the power signal. The problem though is that all the equipment, dishwashers, normal washing machines, hair dryers, what have you, they're not really shielded very well. So you have an environment that is extremely noisy and with a lot of impulse. So although it's doing quite good, still you have a lot of chance of dropouts. And then the phone, you see it's a very low frequencies, and it's also the lower one in speeds. So a little bit on the networking. So wireless N, which is basically the most common wireless solution nowadays. It can go all the way up to 600 megabits per stream. The medium is air. The quality is quite good nowadays, and it's there. AC is the same thing, but a little bit more speed because they tuned and tweaked some stuff, and it will be final in 2013, which is almost now. I mean, we're about to see, as we call it, a second generation of AC chips. MoCA 1.1 has been released some time ago. 175 megabits sounds pretty good. I mean, you can have multiple HD streams over it. What you see is that this technology in the DOCSIS networks is actually being embedded in the chip. I mean, the new Intel TI Puma 6 chip actually has the possibility to add MoCA to it. But it's MoCA 1.1, and the problem we see now is that if an operator is choosing MoCA, they want to go with the next generation, which is 2.0. So the cost effectiveness of having MoCA on board in the chip, and you just have to put some extra stuff on the PCB to enable it, doesn't work. You need an extra chip to do it. HPNA is good, but low speeds. And then you see the home plug AV stuff, which is quite good. But what are we trying to achieve here? I think the biggest growth of CPE in the home is tablets and phones, Wi-Fi devices. So the set-top boxes, everyone wants to get rid of them. You know, the smart TVs, some of them, they try to run them over Wi-Fi. If that's not possible, they try or they run it with an Ethernet wire. But if you look at all the devices, we want a reliable connection throughout the room, throughout the amount of floors, which might be 2 or 3, and a lot of it is without the possibility even of a fixed connection. And if you look at the cable operators, and I mean there are a few people here that are working at MSOs, and they want to have a solution that fits as much as possible every home, and is the most cost effective, because that's what it's all about. So wireless started off, as you see here, in 97. In 99 there was 802.11b, which was a 11 megabit wireless solution. For then, the internet connection, the bandwidths that were given to homes were around the number of 1 or 2 megabits per second. So 11 megabit was a lot of data throughput in the home compared to what you got from outside. 11G came a few years later, 54 megabit, sounded very good, but at some point you saw people streaming longer content. YouTube took off, all those kind of applications, and the need for bandwidth in the home was getting really big. I see that Wireless N is doing 2.5 gigahertz here. It's also a 2.4 gigahertz backwards compatible technology, and they included 5 gigahertz. Now, the Wireless N solution, and you probably all know that, you have 3 flavors. You have a 2.4 only, which is the cheapest. Then you have a switched version, which is either 2.4 or 5 gigahertz, which works fine if you are looking at CPE, at, for example, a set-top box. You can choose 5 gigahertz or 2.4, depending on where your access point is. However, for the access point, I know one operator who had a switchable dual band solution, and they checked it in their systems. They found that less than 2% of their devices in the field were actually switched to 5 gigahertz, because if you run 5 gigahertz, none of your 2.4 gigahertz devices will get connected. And back in those days, and it's probably 1.5 years ago, there were no phones with N, so it was very specific clients that were running 5 gigahertz. Plus, you still had the problem with the distance. And you had the dual band concurrent, which basically is putting 2 radios in. Expensive. I've seen a lot of operators wanting it, but wanting it and wanting to pay for it is 2 different things. So a lot of them started off with, I want dual band concurrent, and ended up buying a single band because they couldn't reach the points that they were looking for. Now is a big year. I mean, 802.11 AC has been around for a while, but that was all draft. So it was a 5 gigahertz solution. So basically what you're looking at now, if you see AC routers, basically they are wireless and on the 2.4 band, and there are 5 gigahertz in the AC band if you see an AC device. What we also have seen is that we call it the first generation AC devices. A lot of the stuff that was defined in the specs, you won't see on those chips. Right now, you see the second generation AC chips coming out, and those have a lot more to offer and actually are a lot better than what AC on 5 gigahertz has to offer. Before that, you see that the current AC stuff and the current N stuff, they don't differ that much on quality of experience, let's call it that. How they behave, how their reaches, etc. Well, the same thing, the speeds all the way up to 1.3 gigabit with MIMO if you use 5 gigahertz. The biggest thing they've done, they have increased the amount of power a lot. I mean, They're now 1,000 milliwatts they can do. They introduced the concept beamforming. I'll discuss that in a few slides from here, which is great because it actually makes the access point a lot smarter, and it can focus and point this 1,000 milliwatts instead of having to act like a light bulb and just spread your energy around. And of course, it can do channel bonding, just as DOCSIS can do. Now Wi-Fi, they started the same concept of adding multiple channels together, and even the 256 QAM modulation is part of the wireless part now. So you see all those technologies. I mean, we heard mentioning of the DOCSIS 3.1 spec. You see technologies from the Wi-Fi space coming into DOCSIS, and you see things that we've been doing in DOCSIS. You see it showing up in Wi-Fi. So, and when we first started having video content delivery over wireless, and cable operators had of course, we're starting to do that through iPads, but ultimately also to set-top boxes. The 2.4 gigahertz band is congested. I have seen some areas, I think it was in Mexico or something. It was crazy. I mean, if you did a scan on the network, the 2.4 gigahertz band, so many SSIDs broadcasted that basically even if it showed you had a good signal, you couldn't get a byte through because it was just flooded. The wireless reach is a problem. If you want to have a set-top box Wi-Fi in your bedroom, one floor up, it probably cannot talk to the access point. So the packet loss, because we didn't have MIMO in the beginning, we were not able to have multiple streams being sent out to see if you could have reflections and have a better signal than just one light bulb-like omnidirectional antenna. And no bandwidth management. I mean, it was best effort. You shout as loud as you can, and you try to push as much data to the client as possible. Where, that if you don't need that, it's probably better to lower the bandwidth a little bit and make it a more sustainable and more quality connection. So we did a lot of investigation, and we saw that, especially in the 2.4 gigahertz band, if you were using N, and you see here we took 150 megabits per second as a benchmark. If you have one wireless device, it of course can use the full band. With 6 devices, the total amount of bandwidth is approximately 20 megabits that they can use. So you already start to lose, and if you go to 10, you see it even drop more. So with multiple devices, the airtime and the time they have available for sending and receiving data drops, of course, a lot because it is a shared medium, and you cannot simply expect every client to have the high bandwidth throughput. This should say Motorola, but I called it ARRIS now. So Motorola actually has a product around for quite a while. It's called a VAP, and they did quite a nice job with it. It's a video access point, and what they did, they sold it in pairs, and actually it shows that you can run, if you buy the right antennas and the right chips and the right technology, and you design it properly, you can actually run good video quality over a Wi-Fi connection. There are multiple operators in Europe and the US that have been using this technology. Some big operators actually have the same wireless technology in their set-top boxes, which is now also ARRIS set-top boxes, so that you didn't have to use them as bridges, but you could have the Wi-Fi technology directly in the set-top box. And we have been showing some really good figures. It is quite proprietary in the sense that it, as I said, it backs off on the amount of speed that you want over Wi-Fi, because you want a good sustainable connection, and you don't care about the maximum speed you could reach. It's using only 5 gigahertz band, so that's basically the band that wireless AC is going to use now as well. And as I said, chipsets and antennas was very important. This thing is a 4x4 wireless and 5 gigahertz solution using MIMO, so being able to steer the signal by beamforming. And beamforming is coming out as a standard in the AC world, and you could do it, but it wasn't, well, it's a bit proprietary there. So the big question also is, how does it work? I mean, how can I say something is good or bad if you talk Wi-Fi? You need to have a reference. I first thought this was Bob Stangioni's house, but apparently ARRIS bought a house in Atlanta, which is huge, but you know, it's all wood, so it's a typical American house. But what we did was quite interesting. There is one place which basically is a turntable, and you can put a device on there, and that device is an access point. And we have multiple points in the house where we measure, and basically we can, by turning the access point, we can measure how this thing behaves and how all the devices are connected and the throughput they have. I hope I didn't put the rest in. No, I didn't, because I had tons of slides with numbers on how different devices are performing, because it's difficult to set a benchmark. I mean, what we did in the past with wireless N solutions, we took the most expensive solution out there and we benchmarked ourselves against it. But now, because we have so many products, as I showed you on the first slide, we can also benchmark between all the different products. And the funny thing is, the combination of ARRIS and Motorola now being one company, Motorola used to be a Broadcom-based company. What they did a lot with Broadcom, we did a lot with Intel TI on the chipset. You know, the Celinos, the Ateros, the Quantennas. We've been developing products with all of that. So it's very nice now because we have all those products and we benchmark ourselves against all those things. And I think that by doing that, we have some very good understanding of how you should do things to start with. So this is a slide which is just important because there is one thing that I learned. Was actually funny. I saw an article where some vendors, and I'm talking retail vendors, they were actually showing equipment on the market that was pretty much outside the FCC approved ranges. You know, they're putting too much power on the antennas, etc. So a lot of people, when they did testing in their lab, this thing performed great. But then they got the first shipment that had to comply to the FCC ruling, and all of a sudden in the field they had a lot of issues. We've been developing, and actually both companies, it was interesting to see that both had basically the same kind of ideas around it. It is very important if you design your Wi-Fi products that you become a good listener. And what I mean with that, tablets and phones, they're all cheap. If you look at the Wi-Fi side, they have a 1x1 antenna array, not even a 1x1 antenna setup, and that's because they don't want to use too much power on their Wi-Fi. So if you have a very powerful access point that can shout very loud, it's good. The phone can hear the access point. The problem is when the phone tries to talk back to the access point, he doesn't hear that because the phone is not strong enough to send all the way back to the access point. So what you need to do is you have to become a good listener, meaning that your noise level of the whole system needs to be very low. And you can do that multiple ways. I mean, one of the things that I guess we're the only one in the market at the moment, we have an internal power supply. Why do we do that? That's because we have to if we know where the source is of any injection of signal, that's good because we can shield the box. The layout of antennas is of course important. We get a lot of help from the chipset vendors. We do our work. We have the home to test it and test it again and test it again. And at the end, we have a good listener as access point. So the performance is not all about, for example, the RSSI numbers, which is a value that you have a really good connection. It doesn't mean much, because you can have a PHY, all green, very good rate, but by the time you wanna have throughput through it, it might be very bad. So again, we've been doing a lot of testing on this, and we've also looked at the measuring everything, and we found that RSSI is not the thing to focus too much on. We did a lot of other things to make, through those testing, the values perhaps a little bit worse than if you would have a retail router, but at the same time, if you look at the amount of throughput we could still reach over the Wi-Fi connection, we exceeded, for example, retail devices. So then a little bit about beamforming, and it's interesting because I once had a guy explaining me this very simple, which I like. The left side is a light bulb. So a typical access point nowadays is a light bulb. And what does a light bulb do? It sends energy to all directions, and if you can see it, it lights up the room, which is nice. But if you look at for example, the antenna of client 1, if it doesn't see the light, it cannot communicate. The beamforming is like a, how do you call these things? A flashlight. You can point, and if I point a flashlight in your face, you see the light. If I don't point it in your face, you don't see the light. But if you have a technology that is capable of steering the energy of the signal to the locations where it needs to go, which is the antennas that are requesting access, you have a good, or at least a better way of putting your energy to the antennas. And you also are a better neighbor. I mean, you are not sending your signal to places where there is no need for the signal. So if you have a very dense environment with a lot of Wi-Fi devices, they can coexist a lot better if they do proper steering of the beamforming. And this is so there are two types. There is explicit beamforming and implicit beamforming. Right now, implicit beamforming is the non-standard way of doing it. We had that on our some of our devices in the 802.11 and 5 gigahertz versions, and this is just a simple number of on and off this beamforming with the phone, and you see that the blue line is exceeding every time, because although it was proprietary and the phone had no clue that there was beamforming used, still the signal was better. So that is the older generation beamforming. In the new AC standard, they have taken this concept and made it, as a standard. So they call it explicit beamforming now. And the idea is that not only the access point understands the beamforming concept, but the client also, which of course means that now you have two flashlights looking at each other. So the overall performance is bound to go better than the older generation. And just for your information, the first generation of AC typically didn't have this explicit beamforming implemented yet. So, that's why I said that the way that a typical 5 gigahertz N nowadays, a good N solution versus a first generation AC solution, is pretty much, almost the same probably. So what is about this second generation? If we look, and this is more talking not about ARRIS, but more about us using and learning from chipset vendors as well. Because if you look at it, chipset vendors are providing the technology, systems on a chip, the antenna layout, etc. But it is up to the vendors to design a product that can actually be used in the field with all the management and the TR69s and all that stuff around it. So if you look at the areas that they have been improving wireless 802.11ac significantly, I think the first, 5 or 6, I mean, it's going to be wider channels. We can go up to 8 spatial streams, but you see 3 or 4 right now developed in the field by the chipset vendors. As I said, the 256 QAM is being used compared to 64 in before, and the beamforming being standardized. LDPC all being implemented. What you don't see right now a lot is this MU MIMO, which is the multiple user MIMO. Basically what you start to do here is you can separate streams. Imagine you have an access point with 2 set-top boxes. You need to deliver different content to each set-top box. The MU MIMO will allow you to actually sort of separate over the air the traffic being sent to the different set-top boxes. They will get there, but right now not many chipset vendors are heavily investing on going there. Another one that is interesting is there is a request at the FCC about additional 5 gigahertz channels to be able to extend the amount of data you can pack in the 5 gigahertz band. It's not been approved yet. It will take some time. You will find some chips that have implemented it. You will also find some chips that haven't yet. So it is it is a move forward, but you will see over time, you will see stuff showing up with more 5 gigahertz bands. What we also see, we don't think it's really going to be part of the access point like the wireless gateway, is 802.11ad, wireless gigabit. So it's a 60 gigahertz frequency, and we think it's going to be mainly used for actually if you have a set-top box and a TV close to each other, and for some reason you don't want to use an HDMI cable, you can start streaming it over the 60 gigahertz. It's in-room, inside, short distance. Again, for access points, we won't see that, but you probably will have the 2.45 and 60 gigahertz implemented in next generation chips. How the cost will look like, you need extra antennas for it, you need to do all kinds of stuff around it. We're not sure. However, there are some TV makers already starting to work on this because they think it is nice, and it doesn't always mean that if the market is there, we will see. And then also a big one is the quality of service, and this is very much a chip thing that I would like to tell you about later. So the market adoption. This is a very new slide, 2013. We got it in. You see that from actually today, which is purple, the wireless and wireless AC. It's a big chunk in AC already. It's only growing. It will become very big, and the top blue is the tri-band with AD. We think it is only CPE and CPE, not really access point kind of adoption for the technology. The market acceptance. You see more and more AC stuff coming up, and it will grow in telephones, etc. What is also important is that there are a few chipset vendors that start to use, as they call it, Internet Application QoS. And what they do, they start to mark traffic, the YouTube and whatever, the over-the-top, actually the delivery from the MSO himself. They start to give it kind of a rating, like a quality of service, like IP-TOS, but not really. It has a server. It is a client server-based solution where there is a classification server that is actually telling the CPE what kind of content it is receiving, and it is handling it with quality of service per that order. So the nice thing about this for a cable operator is that although he probably will never get rid of over-the-top content, if he is doing an IP stream for video on demand, that stream of video on demand is very easily, and it's independent whether it is glass or coax or whatever, he can have precedence over the top traffic. And you can classify it in the system, on the fly. And the nice thing is that there is even some stuff going on where it gets even better, where also the receiving device, I mean, a typical big TV would like to have more, a better quality of experience and a higher priority than a small phone. And there is also some chipset vendors starting to look into discovery of the kind of appliance it's being streamed to. So small phones will have lower priorities than big TVs, because probably multiple people are looking at the big TV, and having a better quality experience is important for a TV rather than a phone. And then I guess this is my my last slide, this band steering concept. So what you see right now, if you have a dual band concurrent device, you have the 5 gigahertz and you have the 2.4 gigahertz. The 5 gigahertz is offering a lot more bandwidth, but the problem is, if you start to use, everyone is starting to use the 5 gigahertz band, it gets occupied again. So through mechanisms of access control list in a CPE, you can actually start the process of, if I have my iPhone and I am in the 5 gigahertz band, but the 5 gigahertz band is getting crowded because another set-top box was switched on, my phone can be pushed back to the 2.4 gigahertz. And my PC can be pushed back to the 2.4 gigahertz. This is a concept that has been around. Everyone is implementing it in the big enterprise access points nowadays. You will also see this happening more and more into the normal home access points. So that is the kind of ways of making sure that you can use the Wi-Fi technology as good as possible, and trying to get rid of power line or MoCA adapters external, because they bring a lot of cost, and if you can fix things with Wi-Fi, that would save a lot of headache with the cable operator. So any questions? Yes. Well, it shouldn't be too difficult to do that, I guess. But well, it was interesting. Just the speaker before me, he was like, "Well, we should have, for the high usage customers, we should make a separate network." And I was thinking about joking, well, try to get them to another operator, because that's the high over-the-top content or newsgroup downloads, the guys that use a lot of bandwidth, they're always a pain for a cable operator or any operator, any ISP.
Exactly, because they haven't paid anything and they want a good service.
And exactly, and they don't want to pay more most of the time. So, but you can, with this mechanism, you can at least make the experience a lot less for him. Yes.
Yeah, I've got several questions. I can't decide which one to ask first, but I think the obvious one for me is I'm a wireless service provider in the rural part of the country where I live, and it's part of our business proposition that we do go into people's homes and help them solve the problem of how they get their broadband around their houses. Mm-hmm. It's intrinsically part of what we do, and we use the power line and various other tricks and dodges to get around people's houses. One of the things that comes up quite frequently, apart from the obvious one of common usage of the same band by people in apartment blocks and so forth, is the hidden node problem, where you've got a house which is perhaps a sprawling house made up of differing building materials, and you find that the wireless access point can probably see all the endpoint devices, but they can't all see each other. And consequently, you then get the hidden node issue where you get invisible clashes, and that can completely destroy the process of trying to have a wireless distribution around the home. Are the later versions of the 802.11 spec likely to address this?
I do not know, but I'm also wondering, are you talking about meshing, or are you talking when?
It's point to multipoint type distribution in a home, where you've got a single wireless router someplace in the home that's appropriate, and they've got a static TV in the TV room at one end of the house, and then son, daughters, husbands and wives have various laptops they wander around with, and you'll find that the laptop at one end of the house can't see the laptop at the other end of the house, so they both transmit at the same time, trying to gain access. It doesn't matter which band they're in, But once they start to do that, then the throughput can collapse quite horribly.
Yes, yes, and well, I think that that the beamforming is helping, and the multi-user MIMO is helping, because you need one device that knows everyone, which is supposedly the access point, and he should be the one also guarding the band and the time it gives to that. So yeah, if you have moving objects in the house, it's always difficult to do that. But I think AC is basically by being better aware also where the devices actually are, because it's steering, it's actually following the moving device, and it's quite nice how it can do that.
Be interesting to see.
Well,
the second question was, which is that we operate in the 5.8 gig band for our distribution purposes from our primary radio stations out to our own client radios.
Mm-hmm.
And we occupy band C, which is the upper end of the band. We have enough of a problem trying to get our channels into band C. I wonder whether, given how much space there isn't in band A and B, whether we aren't going to find that the 2.4 gig experience isn't going to replicate itself pretty quickly.
that is to be seen. You're right, but at the same time, the technology is also hardened in that sense. But the more 5 gigahertz products you get, that will saturate as well. That's why they want to extend the frequencies even wider. But it remains to be seen. But now you have 2 bands, and especially with the steering, you can have the ones that are not so important and don't need that much bandwidth to the lower bands, and keep devices on the higher bands.
Okay,
Well, we'll see how that turns out.
Thanks.
Anyone else?
Costas.
With your MIMO, how do you actually test that particular item based on what you mentioned about noise and keeping your noise floor reduced?
So the noise floor I was talking about is the noise floor in the CP, in the access point itself.
Yeah.
So making sure that it's a good listener. So I'm not sure what MIMO, what you refer to. The antenna layout, the beamforming, the steering is a function of the access point. The problem most access points have nowadays, that they can be heard by the devices, but the devices cannot make themselves known to the access point back, because they're not strong enough to transmit. So
I wasn't sure actually the way that you went through your slide. A lot of your testing seemed to be around running throughput, and I was more in particular interested in whether you started to look at the quality of carriers and how they were transmitted via the antennas.
So there are, yeah, well, the
256 QAM, 64 QAM, which is what you had on your slide.
well, everything we have been doing so far was 64 QAM all the way. Most of it has been N testing, because what we found is that AC wasn't really, the cost that came with AC didn't really benefit from what we could do with N so far. In my opinion, it has been a very, very well-driven marketing gig so far from the retail market to move to AC. But we are also evolving the testing. So we just want to have a very low noise floor in the device itself, so that it is a good listener. And we want to get as high sustained throughput by not peaking every time to try to get the highest bandwidth through. Because you'll see, especially on the fire rate, you already see it, that it's fluctuating a lot. If you just lower, if you set the bar a little bit lower, you have a much more stable connection. That's basically the thing that we found and learned through that testing.
So you don't actually look at the transmitted and the received modulation quality then?
I guess we do. Why not?
That was my question.
No,
All your testing that I saw there was all based on throughput, which is not the best way to actually to look at the quality of carrier, is it?
No, of course, but it's a multitude of things we do. So the testing is basically what I try to explain is that the problem is, what do you test against? There is no reference device, because if I take a reference board from God knows what chipset vendor, that cannot be considered a reference. So we reference now against ourselves, and sometimes against some competition, and then the throughput is important. But how we have been developed the product is not to get, well, we want to get a good sustained throughput, not the highest speeds necessarily.
Have you found that your throughput has improved as your quality of carrier has also improved?
I will check that for you. I haven't seen the actual test reports. I've seen a lot of bars and you know,
Thank
like
you.
that. But I'll try to get that for you.
Thanks a lot.
Maybe just following on from what Costa said there, if you test in the traditional Wi-Fi access points, like a light bulb, like you said, omnidirectional, you can just stick an antenna and some dedicated piece of test equipment to do your measurement. But when you move to a beamforming environment, it becomes really difficult to sort of manually fix a beam in a direction unless you've got really low level access to the CPE to test all those different benefits. It's not really a question, more of a comment. It just becomes increasingly difficult the more and more variables you get to actually get any meaningful testing other than throughput.
Yeah, no, that is correct. But I guess we're evolving our test metrics as well over time with new technologies coming in.
Yes, Chris. Here it comes.
On the question of beam forming, I saw your slides, very interesting that you were able to form the beams to 2 places. Supposing I have 4 devices in the home, then and they're all running, or I need to have signal from it. How does that stack up?
It can do that on the fly. I mean, it's not really a typical device. Is how we make them. We don't even allow more than 32 devices being connected. That's one of the things that we do. But also because you give everyone it's not a fixed beam. You have to share time between the different devices anyway. So the beam in principle is moving really fast to all the devices to have some airtime to talk.
Fine, thank you.
Okay.
Good question.
Showing my lack of knowledge. When you talk about single channel and 256 QAM or 64 QAM, we are talking about just that. And we're not using OFDM or any other technologies.
It will show up in the later technologies, and it has been used here and there in Wi-Fi already, is my understanding. But one of my slides, the new AC will use OFDM as a more robust way of transmitting.
Interesting. I asked because we had a presentation at our standards meeting a couple of weeks ago, which was really all about what MER values you can use for various technologies. But what the practical test that was going on was actually trunking a whole load of video channels, and they did it over something like 240 kilometers of fiber by using DVB-T on an optical network. Just a band of signals, just sort of 50 meg wide, but obviously enough to transport a hell of a lot of contribution video circuits. So here was an interesting concept of using a non-standard, if you like, method. You don't obviously think of DVB-T or T2 for transport on optical fiber. So really I was transposing that onto modems and Wi-Fi access points to see whether that was an obvious sort of next step forward.
I guess it would be stupid if there is some good technology out there if you wouldn't use it if it can be benefit. So you see some technologies just showing up, and I think what you see, Wi-Fi is such a big thing that if the DOCSIS world starts to adopt more of stuff coming out of the Wi-Fi, it makes sense because a lot more dollars are being spent on research there than what we can do in the cable space. So it is a good direction, I guess. Okay, thank you.
Thank you very much indeed.